Induction notes, page 3. Here I have two bare wires connected with some sort of wire or resistance, and I'm going to lay a metal bar across these so you can see I have a complete loop for a circuit, and I'm going to pull that bar to the right. As I do that, you can see that the flux is going to increase inside the loop, and it's going into the page. Lenz's law says the induced EMF is going to go in such a direction that it will oppose this change. So instead of increasing into the page, it's going to increase out of the page. So I'm going to grab that bar with my fingers inside the loop coming out of the page, and it shows me the direction the current will be going counterclockwise around this way. So Faraday's law will tell us the induced EMF off of that. We have a change in flux divided by time. Our number of loops is 1, so we just substitute that in. So I have the area of the loop times the field. And I'll put some dimensions on there. We'll have L and D for our two lengths. And we know that change in D over time is speed. So we came up with BLV is the way we calculate the induced EMF. So what is the force on this rod? We have a current moving through a magnetic field. It's going to feel a force. That is the LIB formula. And we don't have the induced current, but we can calculate it. I know current is V over R. And for the V, we're going to use the EMF. And we just figured out the EMF is BLV. So I'll substitute all that in and combine my B's and L's. And we get B squared L squared V over R. So what is the direction of this force going to be? We're going to use the right-hand rule. So we said the current was going upwards through the rod. So that is my I, and I'm going to have my open hand in the I direction. And then I'm going to cross to B, which is into the page, and my thumb shows that force is going to the left. Practicing Lenz's law. I have a loop of wire. We're inside a field. I'm pulling it outwards. So this flux inside here is going to be decreasing, and it's coming out of the page. The opposite of decreasing out of the page is increasing out of the page. So I'm going to grab that wire with my fingers pointing out of the page inside of the loop, and you can see that the current's going to go around the counterclockwise direction. Loop number 2, I'm pulling it into the field, so this flux is going to be increasing. It's increasing out of the page. The opposite of increasing out of the page is increasing into the page. So I'm going to grab that loop with my fingers going into the page, and it shows the direction will be clockwise. Loop number 3, we're pulling it into the field. The flux is increasing, and it's coming out of the page. The opposite of increasing out of the page is increasing into the page. So when I grab my loop, I'm going to grab it with my fingers in the loop, pointing inside the page. So it's going into the page, and my thumb shows the direction of the current will be going clockwise again. The last one, we're pulling the loop out of the field, so the flux is decreasing. The opposite of decreasing out of the page is increasing out of the page. So I'm going to grab the loop with my fingers inside the loop, pointing out of the page. And my thumb shows that we're going counterclockwise. This will be on our next quiz. Transformers is our next topic. These little things up on the power poles are transformers, and their job is to change voltages. The power plant makes a certain voltage, and then when they are transferring the electricity through the high tension wires, they transfer that voltage up really high, 240,000 volts. And then when it comes back to your neighborhood, they transform it back down to a lower voltage, and then that little transformer that's on the top of the telephone pole is taking it down to 240 volts, and that's what goes into your house. Inside your fuse box, then, they transform that down to 120 volts is what a normal house is. Just about any appliance that we use has one of these little boxes on the end of the cord, and those boxes are also transformers. They're taking the 120 volts that are in the wall and changing it down into 12 volts for your phone or whatever we're plugging into it. It's also changing the alternating current into a direct current. So the way a transformer works, all it is an iron ring, and we have loops on one side and loops on the other side. And remember Faraday's experiment, if we run a current through this wire, through this loop, it makes a magnetic field. It makes a constant magnetic field, and a constant magnetic field will not induce a current on this side. So what we've done to change the field over here, we use, instead of a direct current, we use an alternating current. So the alternating current changes directions back and forth, and that constant change makes our changing magnetic field to induce the current over on the other side. So there's two sides of the transformer. There's an input side and an output side. And I'll make a note on here, putting alternating current through the primary coil creates a magnetic field which induces a current in the secondary coil. So primary is the voltage coming in, secondary is the voltage coming out. So we can use Faraday's law for both of these equations. We know that that change in flux and the time is the same for both sides of the transformer. What's different is the voltage and the number of loops. So we end up with the simple ratio that the ratio of the voltages equals the ratio of the number of loops. I don't bother using a formula when I do these problems. I just look at it. If I have double the number of coils on this side, I have double the voltage on this side. And it doesn't matter which is in, which is out. I could have more coils on this side. If we're going from more coils to less coils, that means we're decreasing the voltage. That's called a step-down transformer. If we're going from smaller number of coils to a larger number of coils, it's called a step up because we're increasing the voltage. End of notes.